Physiochemical determinants of acetylsalicylic acid hydrolysis kinetics affects the pH and temperature. Aspirin is one of the most widely used medications in the world. Millions of people rely on it for pain relief, inflammation reduction, and cardiovascular protection. However, aspirin is chemically unstable. It contains an ester functional group that can undergo hydrolysis, breaking down into salicylic acid and acetic acid when exposed to water. This degradation matters. If aspirin breaks down too quickly, it loses effectiveness, alters dosage accuracy, and can increase gastric irritation due to salicylic acid formation. Understanding how environmental conditions affect this reaction is critical for pharmaceutical storage, shelf life prediction, and even how the drug behaves inside the human body. My research question was, how do pH and temperature affect the rate of aspirin hydrolysis, and what does this reveal about the reaction mechanism? I hypothesized that increasing temperature would increase the rate constant and that basic conditions would produce the fastest hydrolysis and lowest activation energy. This prediction is based on chemical mechanism. In acidic conditions, hydrolysis proceeds through protonation of carbonyl followed by water attack. In basic conditions, hydroxide ions directly attack the ester bond, which is typically more kinetically favorable. To test this, I prepared aspirin solutions at pH 1, 6, and 11. I tested each at 4 degrees Celsius, 37 degrees Celsius, and 50 degrees Celsius. These temperatures were chosen intentionally, as 4 degrees models refrigeration storage, 37 degrees Celsius approximates human body temperature, and 50 degrees Celsius simulates elevated environmental exposure during transportation or improper storage. I used UV visible spectrophotometer to monitor the formation of salicylic acid over time. Because salicylic acid absorbs UV light, I used the Beer-Lambert law, where absorbance is proportional to concentration, to convert absorbance data into concentration values. To determine the reaction order, I plotted the natural logarithm of aspirin concentration versus time. The graphs were linear under all conditions, confirming first-order kinetics. This means that reaction rate depends directly on aspirin concentration. The slope of each line gave me the rate constant K. Temperature had the strongest effect. Rate constants increased significantly as temperature increased, which aligns with collision theory, an exponential relationship described by the Arrhenius equation. I then constructed Arrhenius plots L and K versus of 1 over T in Kelvin. These plots were linear, allowing me to calculate activation energy from the slope. The activation energy at pH 11 was lowest compared to pH 1 and pH 6. This directly indicates that less energy is required for hydrolysis under basic conditions, supporting a base catalyzed mechanism involving hydroxide attack on the ester bond. Overall, my results demonstrate that aspirin degrades fastest in hot and basic environments, while near-neutral conditions provide greater stability. This has direct pharmaceutical implications. It helps explain why medications must be properly stored and why temperature control in transport is critical, and how chemical stability influences therapeutic reliability. My project integrates real-world pharmaceutical relevance with kinetic modeling and thermodynamic analysis to show how molecular chemistry directly impacts human health outcomes. Thank you.